In this video, we're going to talk about the photoelectric effect. But first, let's do a review of waves. A wave is an oscillation or a periodic movement that can transport energy from one place to another. There are a couple types of waves you probably learned about in prior courses. One of these is mechanical waves, which is an oscillation of matter. In these waves, energy is transferred through a medium. These waves come in a couple different forms, like transverse waves and longitudinal waves. And we're not going to be dealing with this type of wave today. Electromagnetic waves, which is what we're interested in, are periodic variations in electromagnetic fields. An electromagnetic wave does not need a medium to travel through. It consists of an electric field that oscillates in step with a perpendicular magnetic field. Electromagnetic waves are transverse waves. Let's talk about the anatomy of a wave. When we look at this diagram of a wave, we notice that we have a crest. That's the top part. That's the top of the hill of the wave. We also have a trough. That's the lowest point in the wave or the valley. The wavelength is the distance between two consecutive peaks or two consecutive troughs. Wavelengths are typically measured in meters. And when we're working with equations, we use the Greek letter lambda to denote wavelength. The frequency is the number of wave cycles that pass a specific point in space in a specific time period, such as waves per second. For example, in this animation, pretend you are standing at this particular point and counting how many waves go by in a second. We tend to measure frequency in cycles per second, which is sometimes abbreviated s to the -1. We can also use hertz, which is simply 1 over seconds, or s to the -1. When we're working with frequency in equations, we use the Greek letter nu to denote frequencies. That's not a v, that's a nu. The amplitude is the magnitude of a wave's displacement. It corresponds to 1/2 the height between the peaks and the troughs, or the distance from the midpoint to the peak or to the trough. The period is the time for one cycle to occur. It's seconds per wave. And the speed of a wave is the distance a wave travels in a certain period of time. How fast the crest appears to be moving. For example, if we were riding on the top of one of these waves like a surfer, how fast would we be moving? We often use the letter v to denote the speed of a wave. Speed is the product of the wavelength and the frequency, and one equation we can use for speed is v equals lambda nu. Speed equals wavelength times frequency. And this could be a little bit confusing because v and nu look very similar. Fortunately, in chemistry, since we're dealing with electromagnetic radiation, our waves travel at the speed of light in a vacuum. So from here on out, our speed is going to be the speed of light, 2.998 times 10 to the 8th meters per second. The symbol for the speed of light is c, so we can rewrite our equation c equals lambda nu. Speed of light equals wavelength times frequency, and this is what we're going to use from here on out. Let's do an example to see how we use this. When strontium salts, such as strontium nitrate, are heated, they give off light with a wavelength around 650 nanometers. This results in a brilliant red light, which looks pretty in fireworks. What is the frequency of red light that has a wavelength of 650 nanometers? 1 nanometer is 10 to the -9th meters, and the speed of light is 2.998 times 10 to the 8th meters per second. Now, get used to doing some algebra. I think one of the easiest ways to work with these equations is to rearrange it first to solve for the variable you are interested in. We are interested in frequency, so we will rearrange our equation so that nu equals c over lambda. We put in our values, and our answer is 4.61 times 10 to the 14th hertz. We could also say 4.61 times 10 to the 14 seconds to the -1. Both of those are okay. Now for some history as we get into the next topic. At the end of the 19th century, most physicists assumed that matter and energy were distinct. They knew that light travels through space as a wave, and that matter is composed of particles that have mass. But in 1900, Max Planck changed all that. Planck was studying the radiation emitted from small bodies that he heated up until they gave off light. What he expected to see was that matter could absorb or emit any quantity of light on a continuous spectrum. But what he found was that matter absorbs or emits energy only at whole number multiples of the value h nu, where nu is frequency, and h is a constant called Planck's constant, which is equal to 6.626 times 10 to the negative 34 joule seconds. He called each of these energy packets a quantum, and he proposed that the change in energy for a system, delta E, equals Planck's constant times the frequency of the light. Planck's discovery paved the way for the discovery of the photon, an elementary particle or quantum of light. Einstein extended Planck's idea of quanta to light itself. Much of his work was based on exploring a phenomenon called the photoelectric effect. The photoelectric effect is a phenomenon in which electrons are emitted from the surface of a metal when light strikes it. The electrons that are ejected are called photoelectrons. These are basically just electrons that are knocked loose from the metal atoms by light. For a given metal, there's a threshold frequency that is needed to eject electrons. If the light is below this frequency, no electrons will be emitted. If the frequency is above the minimum threshold, electrons are ejected. Different metals require different frequencies to eject their electrons. The kinetic energy of the particles depends only on the frequency of radiation that hits it, and not on the intensity or brightness of light. Based on his exploration, Einstein proposed a theory that light is made of photons. In other words, light is quantized, and that the energy of a photon is proportional to its frequency. And this energy can be expressed by the equation: the energy of a photon is equal to Planck's constant times the frequency. Einstein proposed that Planck's quantum is actually a photon of light. If the frequency of the photon is at or above a certain threshold, its energy will be transferred to the electron, and it causes the electron to overcome the forces of attraction that are holding it into the metal. The electron absorbs the photon. As the frequency increases, the energy per photon increases. Hence, the photons of higher frequency light, such as ultraviolet light, are going to contain more energy than the photons of lower frequency light, such as infrared light. On the AP exam, there are two equations you will be using. Combining these two wave equations is sometimes very useful, especially if you are asked to find the energy of a photon that is of a certain wavelength. We can just use algebraic rearrangement and substitution to derive this equation, which relates the energy of a photon to wavelength. You won't be given this equation on the AP exam, but you can easily derive it and use it if you need to. Now let's talk about the electron emission spectrum and the Bohr model of the hydrogen atom. Although the current accepted model of the atom is the quantum mechanical model, the Bohr model still comes in handy when we're talking about certain things, and electron emission spectrums are one of these things. According to the Bohr model of the atom, electrons only travel in very specific circular paths or orbits around the nucleus. These orbits are called energy levels, shells, or principal energy levels. Each energy level is a fixed distance from the nucleus. Electrons have fixed energies in these energy levels. Electrons tend to be arranged in such a way that the energy of the atom is as low as possible. And when an electron is in its lowest energy level, it's said to be in its ground state. Now, if we take a hydrogen atom and we add energy, like electrical energy or a photon of ultraviolet or visible light or heat, the electrons in the atom can become excited, which means they contain excess energy. They will move from their ground state to a higher energy level and go farther from the nucleus. We call this the excited state. Once the electron is excited to a higher energy level, it's in a more unstable position than it was when it was in its ground state. And the electron will quickly fall back down to a lower energy level, which could be the ground state or just a lower level. And as it does this, it releases the energy it took in by emitting a photon of light. And this photon is going to have an energy that's equal to the difference in the energy levels. The difference in energy from the level it jumped from to the level that it went down to. This picture is a simple model of some of the different energy levels possible. The larger the transition between energy levels, the more energy is absorbed or emitted. And this is going to be reflected in the wavelength and frequency of the photon that's released. The higher level and the larger the drop, the shorter the wavelength and higher the frequency. When we're talking about the visible spectrum, higher energy light will be in the blue, purple, ultraviolet range, and lower energy light will be more in the red range or in the infrared range. This release of photons creates an atomic emission spectrum. Scientists can isolate the wavelengths in a substance's emission spectrum by shining light from the excited atoms through a prism, and this will separate the wavelengths through refraction. Otherwise, the wavelengths would all be blended together. Unlike the sun, which has a continuous spectrum like the rainbow, a hydrogen atom will emit only a few wavelengths. The hydrogen spectrum, which looks like this, is a line spectrum and not a continuous one. The significance of the line spectrum suggests that only certain energies are allowed for the electron in the hydrogen atom. The energy of the electron in this atom is quantized. If all energies were allowed, we'd see a continuous spectrum, but we only see lines. Here's an example of emission spectra for several elements, including sodium, hydrogen, calcium, and mercury. We can use emission spectra to determine what elements are present in a sample. The wavelengths of the photons released depend on how many levels the electron drops and which levels they drop down to. An electron that drops across several energy levels will release photons with a higher frequency of energy. An electron that drops fewer energy levels will emit photons with a lower frequency and energy. An electron that drops all the way back to the first energy level will emit photons with a higher energy level than one that drops to the second or third energy level. This diagram shows that the farther the drop is, the shorter the wavelength is and the higher the energy. Not all wavelengths released are in the visible spectrum. For example, the Lyman series, which has electrons dropping to the first energy level, emits radiation in the ultraviolet range. Very short wavelength, very high frequency, very high energy. The Passion series, with shorter electron drops to higher levels, results in radiation in the infrared range. And the Balmer series produces radiation in the visible range. You don't have to memorize these, but I think this is a really nice example of how energy and color of light emitted relates to electron drops. So let's summarize. When a photon is absorbed or emitted by an atom or molecule, the energy that's released is related to the energy of the light, the photon. The wavelength of the electromagnetic wave is related to its frequency and the speed of light by this equation. And the energy of a photon is related to the frequency of the electromagnetic wave through this equation, sometimes called Planck's equation, or the Planck-Einstein relation.